The most common method of absorption spectroscopy is near-infrared spectroscopy. The absorbance of incident light in the near-infrared region of the spectrum, which consists wavelengths from 780 nanometers to 2500 nanometers, differs from molecule to molecule, which yields a unique spectrum within the NIR region of the light due to Beer-Lambert law that relates the attenuation of light to the absorptivity and concentration of the sample through which the light is traveling. Near-infrared spectroscopy measures combinations and overtones of molecular vibrations generated due to the change in the dipole moment of a molecule with covalent hydrogen bonds, such as CH, OH, and NH bonds. The changes in the dipole moment of covalent hydrogen bonds result in Broad overlap bands, as typically there are multiples of these bonds. NIR spectroscopy has advantages such as cheaper NIRS measurement equipment, the ability to measure absorption through thick container walls thanks to the longer path length, and much higher signal level for the same number of photons, resulting in lower exposure times. But NIRS has a major drawback for bioprocessing. It does not generate the same level of molecular specificity compared to Raman spectroscopy, which we'll discuss throughout the webinar. Another common method of absorption spectroscopy is UV-Vis spectroscopy. UV-Vis spectroscopy utilizes the ultraviolet and visible ranges of the light spectrum, which typically consists of 200 nanometers to 800 nanometers range of the spectrum. The molecule of concern changes electronic energy states due to the absorption of light within the UV-Vis range of the spectrum. For the absorption to happen, the energy of the incident light must match the energy of a possible transition between electronic states of the molecule. The transition happens from a lower energy state to a higher energy state, called the excited state. Since different bonds have different energy states, the absorption occurs at different wavelengths of light for different molecules, resulting in different absorbance curves. The degree of absorption is also critical to determine the concentration of the sample, hence the quantification of the sample. Next, let's talk about the luminescence spectroscopy. The most common method of luminescence spectroscopy is fluorescence spectroscopy, where the fluorophore is excited to a higher energy state by an incident photon and then emits light at a different wavelength than the incident wavelength by dropping to a lower energy state. Different fluorophores have different emission spectra, and this method can collect information on fluorescent compounds in the sample. UV-Vis spectroscopy and fluorescence spectroscopy are complementary methods, as fluorescence spectroscopy measures transitions from higher electronic energy states to the ground electronic energy state, whereas UV-Vis spectroscopy measures transitions from lower electronic energy states to higher electronic energy states.